All right, this video is going to talk about IP fragmentation and spend a little time seeing what it looks like in Wireshark when we experience fragmentation. First off, we'll review what fragmentation is and why it's needed. If we look at this Ethernet frame, we can carry 1,500 bytes of data. So we look at this data section, and that's 1,500 bytes. Sometimes, especially back in the olden days, our traffic might need to traverse a link that has a smaller MTU than 1,500 bytes, and it would need to get broken up. But more likely nowadays, you're going to run into a scenario where something else is happening after you send the traffic that's adding more headers to the traffic that's going to cause it to be larger than 1,500 bytes. So for example, you might be doing PPPoE at the edge of your network that's going to add an 8-byte PPP header onto it. So if you send a 1,500 byte packet, if you send a full-size packet, there's nowhere to put that header without breaking that packet up into pieces. Another example would be VPN. VPN adds another header, an entirely new IP header on top of your traffic you're already trying to send. So if you try to send full-size packets that's going to go across a VPN, it's going to need to be broken up. So to get to the end of the story, most of the time you want to try to avoid IP fragmentation. So you'll try to adjust the size of your packets so that whatever headers you're going to add to the end of them on the way out will not go over the MTU so that they won't be fragmented. But we're going to look at what fragmentation looks like in Wireshark. So we have an activity in the class where we're going to send some traffic. This is set up in the lab, so this will work properly in our lab. So first off, we want to send a 900 byte ping with a DF bit set to 192.168.238.2. So if you're in class, you can run it on the computer in class after you've set up your network. If you are using the remote VMs, you need to be on the DHCP network. So the command to do that in Windows, ping-f sets the don't fragment bit. -L is how we specify the size, 238.2. So we want to start Wireshark for that before we send it. So now I'm going to send it, and I get back an error message says reply from 192.168.243.253. Packet needs to be fragmented, but DF bit is set. So in this case, we artificially forced fragmentation to not happen by setting the DF bit. If we look at the traffic in Wireshark, what we see is we have this ICMP ping message we send, and if we look at the flags section of the packet of the IP header, we see that the don't fragment bit is set. So one of the things you might be asked to do on in the future is examine traffic and determine if it's fragmented or not. So in this case, the don't fragment bit is set. So what happened was it got to a link that required fragmentation that I have in the network, and it failed. So this is the ICMP error message. And if we look in the ICMP error message, it tells us what the MTU of the next hop is. So 750 bytes is what the MTU of the next hop is. So if we try to send traffic where the entire packet is less than 750 bytes, it should possibly work. It won't work in this scenario because there is actually no host at 192.168.238.2, so that's not going to work. Interesting thing to me is if we look, Windows Ping normally sends 4 pings, so we sent the first one and it says, hey, we got an error message, and then it tells us 3 more times that it needs to be fragmented, but it didn't actually send the traffic. So if we try to send the ping again, it didn't actually send the traffic. It actually remembered that it needed to be fragmented. I assume at some point this will time out and it will try to send the traffic again. Why this is important to you is if you try to send the ping before you start Wireshark, and you're like, oh, I forgot to start Wireshark, and then you start Wireshark and try again, you may not see the fragmented traffic, right? So it only sent the one, and then it told us the error message a bunch of different times. Same. It's still not sending the traffic again, which I find to be a little bit annoying behavior. So if that happens to you, you can just go up to the next IP. Don't do .1 yet, but go up to the next IP, .3, And now, again, it sent it one time, we got the error message one time, and it's reporting it without trying again. So it's kind of interesting to see what your tools do sometimes when they're trying to be helpful to you. So that's what we see. That's what we see when we send traffic that needs to be fragmented but cannot be fragmented. So what was the result? It didn't work. What was the MTU of the link? That was in the ICMP error message, which I just told you guys. So now we want to send a large ping to 192.168.238.1, and we don't want to set the DF bit. So we're going to send it to .1, and we are going to remove the don't fragment bit. So what's going to happen is fragmentation will be allowed, and then we're going to look at what happens in Wireshark. So we send the ping. It looks like it's working. If we look in Wireshark, we see a ping, we see a reply, we see a ping, we see a reply, we see a ping, we see a reply. So it looks like it's working, but the question is, hey Rich, I thought we should have some fragments. What's going on? Well, yeah, we should have some fragments. And the reason we don't have fragments is because Wireshark, the way it decodes the fragmented traffic is it does not know or detect that it is fragmented. So we need to put a filter on there to show us the rest of the fragments. In that filter, we already had ICMP, so I added or ip.flags.mf == 1. So that's the filter we added so that we will see the rest of the fragments. So now if we look at what's going on, we're sending our full-size 900 byte ping. We are getting back 2 fragments. One of them is one of them is large enough that it fits within the MTU, 750 bytes. The other one is the rest of the packet. So these two frames combine together to make up our IP packet. If you look in Wireshark, it will show you the reassembled. This down here, there's this little tab. This will show you the entire reassembled packet. If you want to see just the part that was in this frame, here's where you can see the part that was just in this frame. So in this case, we have 200 bytes of data and 14 bytes of Ethernet frame, Ethernet header. And if we look at the other frame, we have a length of 728, so that is 28 bytes of header. We have 20 bytes of IP header. We have 8 bytes of ICMP header, and then we have 700 bytes of data. So those two frames go together to make up our full-size 900 byte packet. So if we look at the next step on let's see. Make sure you see the fragments. So we had to modify the filter to see all the fragments. How many fragments was the packet broken into? It was broken into 2 fragments. Were both the request and reply broken into fragments? No. In this case, if we go look at Wireshark, our request was full size, and our reply was broken into 2 packets. So our request would have been broken into fragments on the way to the other host. So the other host would have received 2 fragments, and it sent back a full-size reply, which was then broken into 2 fragments on the way to us. So that's what you should have seen when you do that part. And it says, okay, let's send a packet with a size of 1,500 bytes. So the MTU is 1,500 bytes. So the question is, what's going to happen when we send this 1,500 byte packet? 1,500 byte packet. So what's going to happen when we send this 1,500 byte packet? Well, if we look at our Ethernet frame, we can carry 1,500 bytes of data. So that might make you think that we will send just one big packet to include all of that. But that 1,500 bytes of data has to include the IP header and the ICMP header, which is 28 bytes. So our total data size is going to be 1,528 bytes, which tells me that it's probably going to send it's probably going to break that into 2 pieces and send it fragmented. So if we look at what we're sending, we are sending, if we look, here's what we're sending. We're sending these two, in my case 1296 and 1297. We have one full-size fragment, 1500 bytes of data and 14 bytes of Ethernet header, and then the rest of the data is in this second fragment. So if we look at the IP flags, we have the more fragments set. The fragment offset is 0. The fragment offset tells it where in the packet it needs to go back. If we look at the second fragment, more fragments is not set, and then the fragment offset is 1480. So 1480 tells it where to put that data back in place. So we're sending two fragments on the way out because our packet ended up being bigger than our MTU of 1500 bytes. So we're sending 2 packets out, and if we look at the reply, we're getting 3 fragments back. So this big packet that's getting sent is too large to cross over that smaller link. So on the way back, it's getting broken into two smaller fragments that'll fit across the link, and then we have the third fragment that was the original the original second fragment is now the third fragment because the first fragment got broken into 2 fragments. So yeah, so that's what happened there. You should have seen. Find the sheet. When you do this part, you should see 2 fragments go out, and then you should see 3 fragments come back. So the 2 go out because it's larger than 1500, which is the MTU for Ethernet, and the 3 come back because the MTU of our smaller link is 750 bytes. So you should have captured all of that traffic, hopefully in one capture. If not, you know, I guess you can submit multiple, but you should save this capture for submission. You have to stop it first. So I have the filter ICMP or ip.flags.mf = 1 to show me the traffic I want to see this time. You should save. You should export specified packets and then save them as like lab3 frags or something for submission. So that's what that part of the lab does. If you are like supremely interested in learning, you may be thinking, "Hey, Rich, can we do that stuff in Linux?" Yeah, if you have time and interest and energy, you can go try those steps in Linux as well. A couple things about Linux. By default, the don't fragment bit is set. So if you send a large ping from Linux, it's already setting the DF bit. So the first step, you don't have to tell it to set the don't fragment bit. It does that automatically. The second step, where you want to send a big ping without having the don't fragment bit set, you have to use -m don't. Sorry, I guess I didn't tell you. -s is how you specify the size on Linux. -m don't will set the don't fragment bit, so that lets our. I'll start the capture. The same filter will work on Linux. Linux, again, will keep running until you kill it with a ping, so you might want to kill it so you can actually analyze the traffic. So here we see the big ping going out, the 2 replies coming back. And then I didn't try the super size, the larger packet on Linux. We'll see what happens when we do this. Same. So it's behaving the same as Windows was. We're sending the two 178, 179 are my initial ping going out in 2 fragments, and then I have 3 fragments coming back. So that's what we're supposed to see at that part of the lab, and that's a review of how IP fragmentation works.